uniform distribution, not sure if you remember it, but we went over this, I think it was last time. The uniform distribution has a mean, of b plus a over 2. So in our case, it would be 1 plus 0 over 2, which is 1/2. And that would be in linear units. And then it has a variance, sigma squared, of 1/12 times b minus a, the quantity squared. And I didn't share that with you last time because I didn't think it was that relevant to what we were going to be doing. But I chose the uniform distribution to illustrate the central limit theorem, all right? So what I did is I used the random number generator, so it was for the uniform distribution between 0 and 1. So each of these values in here, like this value is one of 20, okay? Because each sample size was of sample size 20. So each cell represents a random number between 0 and 1 inclusive, and I collected 100 samples. So there's 100 rows and 20 columns. Each row represents a random sample of size 20. So here, right here, this would be like sample 1 going across, sample 2, sample 3, etc. And we go all the way to sample 100. Oh, and let's go ahead and finish up our uniform distribution here. So this one, in this case, again, b minus a is just 1. So sigma squared will be 1/12, right? So anyway, we've got these 100 samples of size 20. What I did is I made a graph of each of the 100 samples of size 20, all right? So anyway, these are just a few that I picked at random. No, I didn't, but these are just a few of the samples of size 20, the way the distribution looked that I picked. And if you'll notice, all right, the mean is like this one's 0.56, 0.58, 0.61, 0.45, 0.56. So they're hovering around the 1/2 mark like we thought they would. Let's look at the standard deviation. So if we go ahead and we figure out what 1/12 is, what the decimal corresponding to 1/12 is, let's see, 1 divided by 12 is, it's 0.083, but remember we'd have to square root that, and that ends up being, lo and behold, about 0.288. We'll just go to the nearest hundredth. We'll go to 0.29. So again, do you see this one is right in line with what we're thinking? So remember we had gotten mu was 1/2, which is 0.5, and sigma is the square root of 1/12, which was approximately 0.29. So if you take a look at those numbers, you'll see that they're all in the ballpark, okay? And remember, they just are sample sizes of 20, all right? So now let's take a look at the next one. So here, this is what I did, all right? So I found the means of all these samples, right? So I made a new distribution that had just 100 means from each of those samples of size 20. And when I did 10 of them, this is what I got. Notice we have the for 10 of them right here, we have 0.49. So do you see that is a lot closer to the theoretical mean? And over here, this was 20 of the sample means, the first 20, and then 0.51, 0.50 for the first 40. So these means are approaching this theoretical mean. And furthermore, look, aren't they getting more normally distributed? Isn't that cool? So now let's also check out the standard deviation. That looks like it's a little bit off, don't you think? I mean, we were getting somewhere around 0.29. So it turns out, all right, what other numbers do we have to play with? I mean, I used samples of size what? Good, 20, right? And so remember that theoretical mean was 0.5 for our uniform distribution between 0 and 1. And the standard deviation we had found to be 0.29. We're looking at values that are more like 0.05, right? But check this out. If I take sigma, and if I divide sigma by the square root of n, where n is the sample size for each of these individual samples, right? Then I would actually be dividing by root 25, and the sigma we had gotten from before is 0.29. And check this out. If we divide 0.29 by the square root of 25, you can go ahead and do it along with me, I get, oh wow, 0.058. And so that ends up being 0.058, and check it out. Doesn't that match our standard deviations of the sample means? All right. So just to recap, and by the way, we often will call that, sigma x bar, right? Because this is the sigma for the sample mean. The central limit theorem tells us that if we keep drawing independent random samples of size n, the distribution of the sample means will be normally distributed with mean mu and variance sigma squared over n. So this is super powerful stuff, right? It means that if enough samples of size n are drawn in this manner, the distribution of the sample means can be approximated by a normal distribution even if the original population is not normally distributed, like we saw with these uniform distributions. So if the original population has mean mu and standard deviation sigma, the mean of all the sample means will still be mu. But the standard deviation of the sample means, which we call sigma x bar, will be sigma over the square root of n, where n is the sample size for all the samples you use to find the distribution of the sample means. So in this here, we used a sample size of 20. We got 100 such samples of size 20. Then we ended up getting 100 sample means, all right? And so our sample means will be distributed normally with mean mu, the same one you started with in the original distribution for the normal. And then it would end up being, for the standard deviation, it would be sigma over the square root of n. Groovy? Okay, so let's do a problem. All right, so assume that SAT scores are normally distributed with mean mu equal to 1485 and standard deviation sigma equal to 345. All right, so to find the probability that we get a score between 1420 and 1510, what do we need to do first, do you think? Good, we need to find our z-scores because we're doing it by hand. So when we go to find our z-scores, what's going to happen? We could remember in general, z is equal to x minus mu over sigma. So z1 we could say is 1510 minus, and our mu was beautiful, 1485 over sigma was given as 345. Cool so far? So just to show you, mu was 1485. We got that from there. And sigma, 345. And then we're getting our x values, so I'll just keep that regular. So that ends up being, did you have time to do the computation? We want to go to the nearest hundredth on it, so with a little work, we get, dun 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 dun. Good, we get 0.07. And then our Z2 is just going to be 1420 minus the 1485, which is mu, all over 345, which is our sigma. And that one was approximately negative, beautiful, 0.19 or negative 19 hundredths. All right. So again, I got these two from the beginning conditions. All right. So, okay. What we're looking to find is a probability, right? So, we need to really interpret the probability that we're finding, right? I know that you're, getting inundated, I'm sure, with Z's and X's and all these things. So the original scale had a mean, remember, of 1485. So one standard deviation away from the mean to the positive side of the mean would be, or above the mean, I guess would be a better way to say it, is 1830. And then if we do another one, we should get what? Add 345 to that one, 2175. Add 345 again. And we get 2520. And then going the other way, what's going to happen? We'll have 1140. And then 795. And then 450. Groovy? All right. So the probability that we were looking to get was what? Good. We want to know the probability that we get a value somewhere between 1420 and 1510, right? So if you look to make boundary lines for this, right? Well, 1420 is going to be what? Maybe about here. Cool so far? And then 1510, on the other hand, will be 0.07. So that's going to be pretty close to here, right? And when I looked at that 0.07, I'm thinking, oh, that's going to be 7/100ths of one standard deviation from the mean, right, is what we got for our Z1, right, for the higher end. So this here was Z1 equal to 0.07, and Z2 was equal to negative 0.19. Cool? And then, of course, if you look at the rest of the Z-scale, what are we going to have? If we could make, literally make another scale under here, and each of these would be, this would be Z, so this is about Z. This would be -3, -2, -1. Over here we would have 1, 2, and 3. Those are all Z values. And the first scale that we had were about X. Cool so far? So the probability that we're looking to find is this one right here. This is like our actual probability that we're looking for, is right in here. And the cool thing is that, what did we learn before? We learned the way to find this was how. So the X scale says we're looking to find the probability that we get we randomly select one test score, and we get between 1420 and 1510. But that, of course, is the probability of what? For Z. Good. That we get between negative 0.19 and 0.07. Good so far? Awesome. All right. So now let's go ahead and look those up using the table. All right. So when we use the table on this, let's see what we get. So that's way over here. So remember that if we have negative 0.19, we're going to be over here. So we're going to be all the way over here, are we not? And so I just did that by, I just did that by meeting up these two values. So I know the Z value is negative 0.19, and I got the corresponding area region, which is this one here, 0.4247. Cool? So right here, that is actually all the area, that 0.47, all right, is all of this pink area right here, right? Because remember that it's cumulative to the left of the boundary point, right? So here, what we're doing is we're finding the probability, keep the colors square, we're finding different probabilities. So we're finding the probability that Z is less than 0.07, and from that we're subtracting the probability that we just pictured, which was that Z was less than negative 0.19. So we found this one to be, what was it, 0.4247, I think, right? And here we need to find the other one. So if we go to the table and we look for the probability that Z is less than 0.07, coming over here, 0.07 would be this top line. Do you see? So we'd be looking 0.0001, etc., all the way to here. So we get 0.5279. 0.5279. And then when you find the difference between the two, we'll get our probability. So just that blue probability we were looking at. But notice that the probability that we just looked at, okay, was this orange one, which goes all the way to the left, right to the left of that boundary line. So it's that blue region we're interested in. So we end up getting this probability, the difference between them, 9 minus 7 is 2, 3, 0, 0.1032, which makes sense, right? That's a pretty small region right there. Good so far? Awesome. All right, so now let's take a look at this one. And it's worth drawing it out again, okay? Because here, all right, again, it's the same stuff, right? It's the same stuff for X, okay? But now we're looking at if 25 SAT scores are randomly selected, find the probability that they have a mean between 1420 and 1510, right? So here, again, you've got your everything going on. Your remember that mu is still going to be equal to, what was that mean? 1485, right? But now sigma is going to be equal to our 345, but we're going to have to divide that by the square root of what? Beautiful, 25, because n equals 25. Okay, so far? So here's the cool thing. So if we figure out what this is, 345 divided by root 25 is 69. And so do you see that this is much smaller? It's actually not even an approximation. It's exactly equal to 69. And so this is going to have way less spread. Does that make sense? So here your mean is still 1485. But this time we're just adding 69 to each, right? 69 to each. So we'll get 15. What would that be? 1574 for the first standard deviation. We're going to get another, when we add another 69, that would be, I think, 1673. And then another 69 will be, we were good. And then going the other way, we would have 1416, right? And then taking away from that one, I'm just going to use my calculator. $13.47 and $12.78. So we would expect our z-scores to have much less spread. I mean, I didn't change the graph on this, right? So, I mean, this graph looks similar, but if you notice, our x-axis has shifted, all right? So now, when we go to our z-scale, so if this one here is our z-scale, right? Then this would be z is 0, and I think I forgot to put that right here, 0. So this one would be 0, 1 standard deviation above, 2 standard deviations above, 3, and then 1 below, 2 below, and 3 below. Cool, cool. So let's check out and see what these different z-scores would be, right? So here we adjusted our values, right? So if we find the z-scores, we're going to have Z1 will be 1510 minus 1485. And this time it's divided by 69. And that's going to be approximately what? Just go ahead and do that. So that's approximately 0.36. Z2 will be the lower one, 1420 minus 1485 divided by 69. And that's going to be approximately negative 0.94, right? So now if we take a look at these z-scores, the lower z boundary is negative 0.94, which is really just one, it's almost one below, right? So here, they would be somewhere around here probably. Oh, that didn't turn out very well. And then, we'd have that upper boundary was 0.36, so that'd be about here. Good so far? All right, so if you take a look at the difference, do you see that's a much larger area, is it not? So now it's still this similar deal with the interpreting the probability, right? But what will happen is we'll get a larger probability. Okay, so now what we're looking at is the probability that, again, that x is between 1420 and really this is not x, but it's x bar, isn't it? They have a mean between, so it's like an x bar or a, yeah, or a mu x bar. No, an x bar, which is less than 1510. Turn would be the probability in terms of z would be the lower one was negative 0.94, less than z, less than, good, 0.36. But then, you know, if we subtract that lower region but from the higher region, what will happen is So that upper probability would be the probability that z is less than 0.36. That lower one would be the probability that z is less than negative 0.94, right? So that one, remember, it looks like this. And if we go back to our z table, and what was it? Negative 0.94. So negative 0.9 is here. And that would be negative 0.90. So 0, 1, 2, 3, 3, 4. 0.1736. Good. All right. So what did we say that was? 0.1736. And then we have that upper one, 0.36 is what we're looking for. So 0.3, 0, 1, 2, 3, 4, 5, 6. Cool, cool. So 0.6406 because it connected, remember, to the 0.06. So 0.6406. And so that's the whole thing. So if I kind of just slightly go over it here, that's that whole thing, the whole region to the left of that top boundary line. But remember, what we want is the region that is not double selected there. Good, 0.4670, right? And so that, whoops, sorry. Me and all my highlights, right? That is this region that we were interested in. So we have this here. Cool, cool? All right, so that was using the central limit theorem. And I do want you to know, the relationship between the scales, the z and x and the z and x bar, as well as how to do these by hand. I will have a part on the next exam where you have to do them by hand. So that's it for today. I hope you have a wonderful morning, evening, or afternoon whenever you're watching this video. Bye. Thanks for listening.